morning, good afternoon, or good evening, everyone, in the Qt World Summit 22. So I'm doing the pre-recording for the World Summit in Düsseldorf in Germany. That's where Axivion is based. And today I'm providing you a little bit more information about Axivion Suite and the architecture verification feature. So my name is Daniel Simon. I'm, as I said, based in Düsseldorf, working for Axivion for over 9 years now. And we are a provider of a static code analysis suite. And one of our key features is the architecture verification, which I'm going to iterate today a little bit more. So let's have first a quick glance at where do we come from and where do we go to. This is our first time at the Qt World Summit, so that you get to know us and maybe we'll see each other again in future. So Axivion is now almost 20 years old. That has been originally spin-off from the University of Stuttgart, and we are now part of the Qt family, in particular the part of the Qt quality assurance tools. So we're looking at static code analysis from the quality assurance part, and that's what we are focusing on. So a little bit of recap, and I'll try to keep that short so that we can advance to the demo. So Axivion is now part of the Qt group, and we are a continuously growing technology company with now over 14 years of experience. Started as a spin-off from the University of Stuttgart. We still have a, let's say, sound academic background with corporations in Stuttgart in Germany and in the north of Germany in Bremen. We have our main development team currently sitting in Germany, and we're trying to expand that, of course, now to worldwide. And we provide support and service locally at your site. In particular, my team is supporting our customers in setting up the Axivion Suite, in integrating Axivion Suite and the static code analysis into your workflows, into your IDEs, into your local workplace solutions, into your CI DevOps continuous build environments, so that you can really make the best out of the static code analysis without having to think too much about how to get it up and running. So we've got a certified quality management system. So of course, we have certification around ISO 9001. What is also important for most of our customers is that we have a static code analysis that is certified according to different safety standards, such as this 26262 as automotive road vehicle safety, 61508 as a generic safety standard, 62304 for medical devices, and the railway standards 50128 and 50657. We have, as of now, more than 200 customers worldwide. More than 10,000 users are in daily use of Axivion Suite and work with the results of the static code analysis from us. And we have references across all different industries with technical software. So as the title here of this slide says, we're taking care about software erosion protection. So we're trying to stop your software erosion. The software erosion sometimes is also referred to as technical debt. So things that creep into your software over time and deteriorate the quality of your software. We are tackling that and try to keep up the quality of your software despite pressure in the projects and the daily hassles. So I just brought a list of our reference customers with me. So as you can see here, that some of our customers are on this slide. I have more, of course, references on our homepage when you want to look at more details. We have some success stories there. Software erosion matters across all technologies. So software erosion will also happen in Java, in C++, in C code, in you name it language. It will still work. And our focus with our customers is on the C++ technology world, and then in different branches of business. So we have a quite strong base and footprint in automotive. We have a strong footprint in medical, in automation, in everything that has some more or less technical software. And of course, there's already quite a large base of customers who also use Qt, and the combination of Axivion and Qt now will leverage that common base of customers and also expand our features to new customers. Okay, so to give you a very quick intro into how Axivion Suite works, so that you can follow the demo later on, is we assume that you have a development team in place that starts in this lower left corner here with a bunch of people using their IDEs, doing the programming work. And as soon as you have finished your programming on your local machine, you will then commit and push to your version control system of choice. So that could be anything from Git to Subversion or ClearCase or Rationality Concert, MKS, and you name it. And from that central version control system, a lot of people nowadays have something in place that's called a continuous integration, CI, DevOps continuous build. And the usual way forward here is in the base use case that we run the continuous integration on a nightly base, on a event base, like push to a branch, pull requests, something like that. Axivion Suite then checks your code. You can think of that like we compile the code to our own Axivion format. On top of that Axivion format, there's no more executable code that comes out of the Axivion Suite, but that's Axivion Suite internal representation that we use for different analyses. So analysis, I will elaborate on that in a few seconds. But the key thing here is on top of that information, we can run, for example, our architecture check and programming guidelines checks and others. If you ever have used a static code check tool on a legacy code base, you know that if you run it for the first time, you will end up in tens of thousands of issues. So that this is not overwhelming you and killing you in your daily work, we have built in a delta computation. So we assume that you have a continuous integration up and running. So we have repeated analyses over time. We get in touch with a version control system, and we have a memory in here that keeps or that allows us tracking issues over time. So we do not report the same issue again and again and again, but we can report the deltas and the differences, and that's what we call the delta computation here. So this delta computation after an analysis run will check what issues have been there before and then report it back to the users. By the way, the users can usually be identified by means of the version control system. So we can send out very precisely the emails, oh, you did something wrong, you please fix it here, or there's things you need to reconsider then. So in the easiest case, you just click on that email. There's a link to the web UI or to your IDE interface. So we have IDE plugins for Qt Creator, for Visual Studio Code, and Eclipse-based IDEs and so on, or even VI. Could use that if prefer VI. And then we have the web user interface where you can watch the results from the nightly build from the last feature branch build and directly see the results and the effects of the static code analysis and the architecture check into your web UI. And of course, we have also a means of reporting. So if you need the results from the analysis for an audit, that is the way forward. Finally, what I want to mention is that there's an input and output possibility into this delta computation also for third-party tools. So for example, if you use your GCC warnings, you can use your Doxygen results, or you can use input from other tools, test data, like coverage information from Swish, Coco, and you name it, so that we can integrate also on a very high level and immediately make use of this delta computation. So that's one of the key things. This is also very convenient if you have other third-party languages that you want to benefit from the delta computation. Okay, so now a little bit more to the features that I wanted to show you. We have different features in Axivion Suite. At the core, we have a scalable platform for static code analysis and defect detection. This is, let's say, the commodity thing. You need to have that in place with a high precision, and we're really proud of that precision that we can offer our customers. And on top of that, we have built a number of different analyses that are useful in daily work. So for example, we have the architecture verification. That is checking your architecture. We have the clone detection and clone management. We have the metrics monitoring, coding guidelines, state code analysis, and cycle detection. Today, I'm going to focus on the architecture verification. So this is now the way forward to specify a quick run through how architecture works. So let's just consider you have to create a new project on the greenfield. You usually start out with an architecture specification with boxes and arrows. Let's assume you have a 3-layered architecture with an user interface written in Qt. You have a business logic in between, and you have the hardware abstraction down there that has temperature sensor with degrees Celsius. So simple example in my daily life is my car. We have temperature sensors for the outside temperature, and I have a warning light in my cockpit that tells me when it's 0 degrees Celsius or 4 degrees Celsius to warn me of road ice. Now we start implementing that stuff. So we are studying coding, and then the product manager comes along. We are not yet finished, but we have a prototype, and he now needs that tool or that prototype to demonstrate on a trade fair tomorrow. Lucky for us, we can now, of course, program a lot of things, but our colleague B is on leave. He's not there. So we have to do a workaround, and the UI directly accesses the hardware abstraction, which is, of course, erosion because it's now no longer documented. And the zigzag line shall indicate that this is not seen in your architecture anymore. So let's go to the next step. What are the actions here? Well, your product manager is happy, developers are happy, no actions taken, but we have erosion built in the system. So the decision was very clever, but it was just erosion. In the next step, your product manager comes back from the trade fair and says, I sold this prototype a million times, but not in an area where we have degrees Celsius, but in the US where we need degree Fahrenheit. As an architect, of course, you can say, oh, I've already anticipated that. I have this working instructions for my colleague from B. He's now going to implement, or she's going to implement the conversion. And then we can start continuation of the project. We can also sell it to the US. Now, at the end of the project, you usually start testing. So you do some unit tests down here. You do the hardware abstraction works. You do the conversion test works. And then at 32 degrees Celsius in summer, the red warning light starts to flash. Now this is obviously a bug, and you do not see that red line here. So now you have to work under pressure. You don't have time to do a proper fix and analysis. What could be one of the solutions here? Well, you just know that this code here in the green box already works. So why not just copy it over? Now we have a workaround, quick and dirty. Quick is good, but dirty will stay. And here we have now duplicated code. We have more erosion, and this brings the system at some point to an unmanageable state. Let's now tackle that problem with the Axivion Suite. So the first step would be we draw that architecture in a way that it's machine readable. So with boxes and arrows, we have the same ABC. We do a static code analysis, so we know everything about your code, and we can directly and immediately flag this deviation from the expectations. Then the developer and the architect can discuss how to proceed. So one possibility would be to remove the deviation in source code, so that fixes the code, and then we have architecture and code in line. We could also document it, or we could accept the deviation for the time being. Still, it's there and it's visible. So in the three cases that we have here, we have in case one, we've corrected the source code, architecture is in line with code. In case two, we have updated the architecture, then architecture is in line with code. And in case three, we did not do anything, but the deviation is accepted temporarily. And then still the architecture plus the deviation is in line with code. So you have no more surprises as plan and implementation are in sync, and assumptions are reliable for your future work. So that's a very quick run through this. So you will hear the same story again by doing that in the demo. So now it's demo time, and I'm going to switch over to the virtual machine to demonstrate it. So hello and welcome to my Axivion Suite demo virtual machine. Now we are going hands-on into the exercise of recovering an architecture from an unknown project. To give you an idea of what we are doing, I've analyzed the source code beforehand. So what I can show you now is the results from an analysis of a piece of software that's called ISO AGlib. ISO AGlib is an open source project where they implemented in C++ an CAN communication stack. So I set up this analysis, ran it in the background, and got all static code analysis information from the system. Again, here we have architecture, we have duplicated code, we have cycles, we have dead code analysis, we have a metric analysis, and we have some style violations. Here we're going to focus on the architecture part of the project. So switching back from my analysis, I'll show you a quick overview of the architecture of the system. Now, my step here was needed to go to their wiki, and in their wiki, they have a documented architecture, roughly like in our previous examples with layers, boxes, and arrows. So on this first glance, we see that they have documented different layers, starting at the top with a communication layer. Then we go to the driver extension layer. We have a hardware abstraction, as in the previous example with my temperature sensors. And finally, down there, we have hardware and drivers. So hardware and drivers are not part of the source code analysis. This is some really, really low-level stuff that I cannot analyze as it's not C++ code, but starting from the hardware abstraction and upwards, we have C++ code available, and that's what I have the analysis for. So to structure that analysis, that tool, they provided, in addition to a source code structure, they provided this 3-layered architecture. They have different boxes. As you can see here, that's the layering from left to right. They have boxes in there with different names in it, different colors, and they have different types of arrows. They have different types of, well, they have even a hovering box here that's called scheduler. So as I'm trying to understand their architecture, I would have asked them, if they were available, what do your different colors mean, for example? Do the green boxes and the blue boxes have some communication things in common? Why is it that I have a blue part here, a yellow greenish part here, gray parts over there? Is this templates? Is it not implemented? What do the arrows mean? Is it data flow? Is it function control flow? And why do we have different arrows that some start in the middle of a layer? Some go from box to box. Does it mean that the box is only allowed to talk to this box, or does it mean something different? Then we have this layer to layer or layer to application layer box arrow. In particular, that's something confusing, but let's start and give it a try. Just go for trial and error. So in the first place, we now have the architecture in a non-machine readable format. We have some place with a static code analysis results, and I'm now going to show you how we can bring things together into one tool and then run a static analysis against the architecture check. So let's switch over now to a tool that is part of the Axivion Suite. In this tool, we have possibility, first of all, to model an architecture. So what I would now could start doing is we create, in a very simple way, simply the picture on the right. So it's communication, we have a driver extension, maybe a HAL, and maybe we have some drivers. And from my experience, I know that always there's something like a MISC package. Now, these are the boxes. Now we can use the arrows where we say communication is allowed to talk to driver extension, is allowed to talk to drivers. No, let's go to hardware abstraction. And I think this one was not, just remove it again. So that's it. And maybe there's something that we can call MISC, and everyone is allowed to talk to MISC. So that would be the easiest way of creating the architecture. And in our case, I already prepared something for the sake of the workshop now, or for the sake of the presentation. So this is now very simple, and now we have a high-level architecture. Of course, this is not very precise, but let's have a quick look at how we designed it in more detail. Do you want to save it? Yes, thanks. And here we have a more closer picture that is more resembling the architecture as they defined in their wiki on the right side. So as you can see here, we now have a communication layer, the driver layer, the hardware abstraction layer, the scheduler, the utilities, and the configuration layer. So that is roughly what we analyzed from a good guess. For the sake of the exercise, we can now just add another component here and assume that there's also a communication from communication to other component. As you can see, I modeled the scheduler as a component separately out of here, and I guessed that communication and driver extension are allowed to talk to them Yeah, and that's my first approach to the architecture. So on the right, we have the non-machine readable format. On the left, we have the machine readable format. That is something that you can derive directly from documentation or from the discussion with your architects, with your experts of the system. So now we have on one side the high-level model as a graph. On the other side, we did an analysis for the source code from the static perspective. I'll show you around that a little bit in more detail. So what you see here is the base data that we can derive from the static code analysis. So all the nodes in here are different artifacts as they're called source entities. So for example, these nodes represent macros, members of structs and classes, global variables as constants or variables. We have things that we call routines, so callable things like C functions, C++ function members, virtual functions, constructors, destructors, things like that. And there's, of course, classes and interfaces. There's templates available in this schema for the graph. From the perspective of all those nice edges between the nodes, we have modeled all source dependencies here. So for example, what we have in place is we can just hide all, so it makes sense to see the different things. We have, for example, function or call relations between things. So call relations can be implicit or explicit. In C++, an implicit call is, for example, if you have a class type object on the stack, it will call the constructor at entering the scope and destructor when leaving the scope. So that's an implicit call here. Explicit calls are some things that you as a developer write if you want to have the call. Could be, for example, a very simple static call. That's the most part of it. We have some dynamic calls that are calls through function pointers, and there are some calls through virtual functions. So that is runtime decided what is really called. And in that case, you now can model all the function calls. So callable things can be called in different ways. There's a lot of other dependencies available to for our use, but currently we only look at the calls. So if you turn on everything, then we get back to that big ball of mud. Probably also your project would look like that. So this is not something we really look at. It's just to demonstrate that we have all information available. I close that tab now, and let's go back to the architecture. So now we have a high-level model. We have the low-level model of the source code. Now we need to bring that on top of each other. And this is done by so-called mapping. So the mapping is mainly going through the structure of the source code on one side and the structure of the architecture on the other side. So for example, I've prepared that a little bit. We can now map the driver extension in a folder that is called driver in the source tree. So when you look at the source tree directly in the file explorer, we are now inside the ISO AGLib, and there's a driver folder. Driver sounds to me as a human being, sounds like driver extension in the architecture. It's not exactly the same, but it's close enough for me to guess. Same for the COM folder, so that's probably the communication layer. HAL sounds like hardware abstraction layer. Scheduler is scheduler. And then there's something like utilities that are already modeled. So we now need to map that in the Axivion Suite. So we just take the communication layer, drag it onto the communication component, and let's do the same for the utilities. And currently I don't have anything else left for the other component because that was just for the exercise. And we can now also have a quick look at the game that we play here. So we can now drill down up until the contents of the files. So that's the structure of your code, and everything that is now below the driver extension, the driver folder is considered to be part of the driver extension. That is now architecture, source code, and the mapping tells us how to put that on top of each other. And now the architecture is merely looking through those two layers and showing you the differences. So we're now ready and set. So we go back to the architecture layer, and let's run the architecture analysis. So we perform the check here, we run the analysis, and this is now in real time. We execute the analysis and we get the results. So the results look pretty similar to what we have as a blueprint here. So we have the architecture and we have the results from the architecture check. It's mainly taking over all the nodes and the edges, and now it's coloring the edges a little bit. So here we specified in the architecture that communication is allowed to talk to scheduler, scheduler is allowed to talk to communication, and the arrow has now turned green, which means that we found some evidence in the source code that this is really implemented. So we allowed the communication and we found evidence for the communication. This other component here, it's a slightly different thing. We specified in our architecture that there should be a communication between communication layer and other component, but there is no such thing because we did not specify any source code, so the analysis could not find anything. And now this gives us a yellow edge, which means it's an absence edge. So we specified but did not find any evidence for a dependency. So this is now we can already fix it simply because we can just delete this node and it will be gone. And for the next run in the analysis, this will disappear. Let's check further things. So communication talks to driver extension, talks to hardware abstraction. Let's put that side to side again with the architecture. So that is what I expected, that it's top-down communication. But in reality, it seems that there are also backward arrows. That is one thing. And there's a direct dependency from communication to hardware abstraction. So talking about the direction of the dependency, that's somewhat difficult because, of course, I do not know what the semantics of their drawing here are. And it could be also the other way around. So let's have a quick look now at these divergence edges. So we did not expect that. I just double click it. And here we go to the list of underlying causes. So you have usually to read that from left to right. So we have now a violation, which is divergence, meaning there is a dependency, even though we did not allow it. It's from driver extension to communication layer. We have a total of 24 underlying causes. And then we go into the source code. So we have now things in ISO AGlib namespace in a certain name, have a certain class, and this class declares something that is in our communication layer. So easiest to spot is usually our static calls. So we have an ISO AGlib operator, right shift operator that calls something in the ISO AGlib namespace that is part of the communication layer. So that is some pattern that we now can see. Oh, it's 24 violations. Maybe that's good or not. Let's have a quick look at the source code here. So we double click, we see the source code of the system. It's now here, operator right shift does something with RC data input string. This RC data is an ISO name and so on and so forth. So that's the reason for the violation. So now can decide, is this truly an architecture violation or is it something we can redocument in the architecture? Depending on the semantics of your system, this should be something that we change in source code. If not, we can now easier change the architecture than change the source code, of course. So that's what we are going to do. Let's close those two views again. Let's go back to the architecture specification. Let's iterate over that. So we allow now dependencies from down to top. So that's the meaning of the arrows. Maybe let's have a quick look back to that arrow from communication to hull. So that seems that it's allowed to cross the different layers. And let's double click it here. And oh yeah, we now see we have a divergence from the communication to the hardware abstraction with 166 violations, which for me as a human is an indication. Maybe they did not really want to have the layers opaque, but you can just call it through. So again, for the easiest fix, we fix the architecture here and say it's allowed for communication to access the hardware abstraction layer. Now we found in the course of reading through source code that there's a utility package in source. That is something where I would say utilities are usually allowed to be used by everyone. So as we have it here, so all incoming dependencies are green, but utilities should not use the application, should they? So we have a more precise look at this list. So the violations here are obviously some conversion of streams with an operator, but if you look at the amount of violations, it's a very small number. So we now roughly have nine deviations, and this is something where I would say, oh, it's probably an architecture violation, so we leave that in. So in our case, the ideal architecture is already what we've documented, but leave that deviation in the architecture and just live with different violations. So the developers have to fix that tomorrow. So let's now rerun the architecture check. We added a little bit around the communication, or we added a little bit of dependencies. We could, of course, also play around a little bit with the mapping if we mismapped some files, some components in the architecture. For the exercise now, we can simply continue with the architecture check, second iteration. We run the analysis, again, with all the default settings. We run it, we resize it. And here we go. It's now much greener than before. Of course, the exercise is now a little bit artificial, but it's not the ultimate goal to have the architecture recovery being all green now. It's okay if there's some violations in there. We now want to define the ideal architecture that we expect. And for the future, we could now move the source code more towards the direction of the architecture as intended. So this is now our local workflow. We do the iterations until we have reached a point in the discussion where we say, oh, this architecture is now okay. We want to go for that. And then we can take the output from that architecture, so this high-level architecture definition plus the mapping. We export it to the continuous integration, and then we can reuse it. So for doing that workflow, we will now export this as a GXL file. I already did that as preparation. So we have now a high-level architecture. We have a high-level mapping exported. We have a low-level architecture and a low-level mapping. So these files are added to the analysis configuration. That is part of the ISO glib configuration for the source code analysis. Will be picked up by the next continuous run when we commit that architecture as code to the repository. And we will then see the results in our web frontend. Before doing that, that was usually something that will run a few minutes. And I've prepared everything. Let's just cancel it before we go to the final results inside this architecture. I would like to show you that this is, of course, only a very lightweight way of the architecture that we had here. We can also refactor it or rework on this architecture by using hierarchies, by using more detailed views on that. And this picture is now much closer to the original PNG documentation in the wiki. But of course, it takes a little bit more time. So 5-6 boxes is some few minutes. This is a little bit more thinking and setting up and a little bit doing more in the mapping. And this can be implemented very easily. We externalize it, and we now have 2 architecture checks actually available for our continuous integration. So to complete that cycle, we exported that architecture in the form of a machine-readable format as an XML file. We can now use the Axivion config tool to add low-level and high-level architecture to our continuous integration cycle. If this is set up correctly, we can then run the system. It's usually going through our Jenkins or your GitLab or your continuous integration system. And then we end up in the results for the end users. So when we do not change the configuration anymore, we end up in the web browser-based analysis. And here we can look for the architecture violations. So what you see here is that in total, from the current status, we have 448 different violations of the architecture, which is quite a lot. We have split that up into architecture low-level check and architecture high-level check. And this is a long list of issues. So all the individual issues that you've seen in the Gravis tool interactively are now also interactively available in the web user interface. Here we can filter for owners, we can filter for parts of the system, we can use a lot of different other features here that I do not want to show right now in this session. One important thing I'd like to mention again is that this is 448 is quite a lot of things to do. We can also restrict that to what has happened between the previous and the current run of the analysis. So somewhere between 2019 and the current analysis, somebody has added 2 divergence edges, one in the high level and one in the low level check. And of course, this is now a place where if you're alerted that there is now this one single violation in addition to everything else, you can really work on that. And you can now drill down also in the web browser, so you do not have to start Gravis and all the complicated things, and you do not have to be the architect in that place. But we have a view on the source code here. So left and right, this is exactly the version of the code as of September 2022. You see the caller and the callee, because in this case we have a static call divergence. You see the context of the architecture violation. Some task controller component talks to common system, AC something. Yeah, that's the view that you have as an architect and as a developer. And now you can start discussing if we have to change the source code or if we have to change the architecture again, and then go through the iteration. So key point here is we do not have to look at the perfect world, but we can simply have a quick look at what has changed since the last run. Of course, you can also improve over time, but as I have no control over their development in that project, this is rather difficult for me to change the source code and get it upstream again. Yeah, that's the overall workflow through our analysis. So we do an analysis, we use Gravis to model the architecture, to save the architecture, to maintain the architecture. And then if the architecture is our fix point, we can add that to the analysis in the nightly runs, in your pull request, feature request based runs, and then check if you're working into the right direction. Now, maybe one more statement around this. How do you model this architecture? So Gravis is the no frills approach. It's really boxes and arrows, and that will be sufficient for quite a lot of customers. So it's better to have a very simple architecture than to have no architecture at all, because that gives you now a language where you can really talk about things that you could not talk about before. Quite a significant number of customers has already a model of their architecture in place in different tools. So then the solution is, for example, if you look for enterprise architect models, I remodeled the ISO AG-lib model of the architecture also in enterprise architect. We do pretty much the same. So we do the boxes and arrows approach. And there's, of course, in the UML language, more boxes and arrow types available. But the basic principles are the same. And then you can translate this UML model via XMI import interfaces. Or what is a communication? What is the scheduler? What is the how do they relate to each other? What does this UML dependency arrow really mean in source code? This is something that you should clarify anyway with the developers, because otherwise they will do anything. And now the architecture check makes sure that this fits all together. So you can also simply use an export from the enterprise architect model. Then Gravis becomes more as a debugging tool in the background. So we don't use the Axivion tool anymore to model, but we just go directly from the enterprise architect or from Rhapsody or from you name it UML tool into the analysis part, and that will be fed back into the browser-based approach. Yeah, that is the final step in here. So modeling, executing the analysis, running it, and it really brings your architecture models to life. So it's no longer something on the flip chart, something in a PowerPoint file that will deteriorate over time and that the source code holds the truth. Now we also have the architecture and the high-level model as a truth. And just remember that is the difference between the high-level architecture, where we know the structure of the system, and that wonderful, colorful view on the dependencies of your system, where we really have to look through everything because nothing makes sense. And that's the big game changer here. So going through that, we end up finally in our CI DevOps environment in the architecture view of the web user interface, or it could also end up in your IDE, directly feeding back that information into your Qt Creator, Visual Studio Code, or Visual Studio, or you name it plugin. Yeah, that's basically end of demo time for this session. So taking you back. So, dear listeners, demo time is over for today. But of course, if you are interested in the architecture check, as we did it with Axivion Suite, and how to model, when to model, how to implement, and how the other features of Axivion Suite work and could work for you, please get in touch with me or one of my colleagues from Qt. My contact data you find on this slide. So the formal address is somewhere based in Stuttgart in Germany. I'm based in Düsseldorf in Germany, and I would love to hear back from you and also get a little bit of feedback how this works and how this could work for you. Thank you for being here. Have a nice day, week, and hope to hear you soon. Bye-bye.